Okay. All right. I was just looking at the outline. I had set up a very big agenda, I guess, so I'm not going to do as much, particularly because I'm supposed to cover a little bit of heat and mass transfer as well in this course. So turbulence, hopefully we will touch a little bit about what the nature of turbulence is. And dispersion, I think, is an important topic. We'll touch upon that. But today what I'm going to do is talk about thermal boundary layers. Okay, so it's basically an extension of momentum boundary layers, the Prandtl derivation of the Prandtl boundary layer equation, the Blasius solution, the von Karman analysis, the integral analysis, are all important topics in boundary layer. Now, there is a whole book by Schlichting called the Boundary Layer Theory that talks about momentum, heat, and mass transfer, laminar and turbulent boundary layers. So it is again a very vast topic. Boundary layer control is another topic. So we are just scratching the surface in some sense of each one of these areas. Stokes flow, creeping flow, potential flow, boundary layer flow, etc. So we very quickly in the last class we looked at the Blasius solution, and the concept of a local versus average friction factor is very important for you to understand. So the local friction factor we derived from Navier-Stokes through Prandtl boundary layer equation as 0.664 divided by square root of Reynolds number. We get the functional form of how the friction factor changes with Reynolds number. And in heat transfer, we would be interested similarly in how does the Nusselt number change with Reynolds number or Prandtl number, which is what we're going to do today. And in mass transfer, the same idea, how does the Schmidt number, which incorporates the mass transfer coefficient, the Nusselt number incorporates the heat transfer coefficient, friction factor incorporates the drag force. And we saw that the average friction factor averaged over a certain length. So the only difference is the functional form is the same. But if I put L, that means it is averaged over the total length. X means a local value, X1. What is the friction factor at that point? And obviously that expression tells you that the friction factor is infinite at X1 equal to 0, then leading it to the plate, which we saw in the last class as the reason because there is a discontinuity. The velocity gradient is very infinite in some sense. So the friction factor is high. But it will very quickly come down as the distance of the plate increases. And that analysis that we did, we saw is valid only up to a Reynolds number of a finite value, 2 times 10 to the 5. It's always the case. When you make certain assumptions, that assumptions are spontaneously broken by the flow as you keep increasing the forcing term, which is the Reynolds number in this case. So the flow becomes turbulent. The turbulent boundary layer evolves from there. We also saw how the boundary layer thickness changes as constant divided by square root of Reynolds number. And I just gave the Faulkner scan solution as a reading assignment. And then we went through von Karman integral analysis. So there the concepts of what is a displacement thickness, what is a momentum thickness, and how do you integrate the Prandtl boundary layer equation in the vertical direction. So you lose information about your ability to predict what the velocity profile is. But if you input a velocity profile, like the one example that we did in the last class, and we're going to do another one today for thermal boundary layers, then you can predict what the friction coefficient would be and what the boundary layer thickness will be. But the coefficient that you have, like 4.64 or 0.646, depends on what functional form that you put for your velocity field. Here I've taken an example of a cubic. You should be able to do, for example, in an exam where I give you a sine of y over delta or any other function. You should be able to go through the mechanics of taking this, putting it in here, solving for delta, and then solving for the friction factor. Okay, so I'm not giving you assignments. I think we are approaching the end of the term, so I'll probably give you one more assignment at the most. And but you should read all these as a preparation for your final exam. So what we want to do, this is a material taken from chapter 12.4, section 12.4 and 20.2. 12.4 deals with thermal heat transfer problems. 20.2 deals with mass transfer problems. Okay, so our problem is we have a two-dimensional flow field, and the geometry is, as before, a flat plate. Okay, and you have fluid approaching that flat plate. We know that the fluid forms a momentum boundary layer. Okay, now in addition, the plate is at a different temperature than that of the fluid. Okay, so in this particular case, we are going to say that the plate is at a temperature of T0 and the fluid is coming in at a temperature of T infinity. Okay, so when that happens, the question is, how does the heat transfer take place in that boundary layer? So there is already a momentum boundary layer, which we indicate as delta, which is a function of x1. This is x1 direction, and that is x2 direction. Okay, so in addition, we are saying that we have heat transfer that is taking place. Okay, so there are two cases that you can consider. One is T0 is greater than T infinity, the other one is T0 is less than T infinity. Okay, but think about it. What do you think would happen physically when I have a plate that is at a different temperature than from the fluid? And the plate is maintained at a constant temperature throughout.
There will be transfer of heat by conduction in the boundary layer, and the other side will be convection from out.
Right, there will be a mechanism of conductive heat transfer in this direction, and as soon as the heat is transferred in the direction, it's going to be convected in the horizontal direction. Of course, conduction will also take place in the horizontal direction, but in the boundary layer context, we are going to ignore that. Through a scale analysis, we'll come to the same conclusion as we did for momentum diffusion versus momentum convection. But under the assumption that we have a two-dimensional flow field and two-dimensional temperature field, two-dimensional concentration field. So the omega A here is the mass fraction, for example, of a particular species. So here you have to think of the plate as being made up of a naphthalene ball, for example, a naphthalene sheet. Naphthalene can sublime into the air. Okay? So you'll have a mass transfer by sublimation. Or you can think of that plate as being coated with a thin film of methanol or ethanol or whatever material that can evaporate. Okay? So there is a mass transfer that can take place from such a horizontal plate, and that is governed by, again, diffusion and convection of the mass, the species. The species here is A. Okay? And similarly, the heat that is being conducted and convected is governed by the energy balance equation. So under those assumptions that there are only two velocity components, V1 and V2, V3 is 0, and they depend only on x1 and x2, you need to go and simplify the continuity equation, which we have done before, and you simplify the Navier-Stokes equation, the full Navier-Stokes equation. Okay, so here you get convection in both directions, and here you have the diffusion of momentum in both directions, the pressure gradient. Now, can you identify for me what this term physically means? G1 beta T minus T infinity, G2 beta T minus T infinity. What could that potentially, what mechanism could that represent? Where does it come from in the Navier-Stokes equation?
Beta is the thermal conductivity.
Beta is not the thermal conductivity. Beta is the coefficient of thermal expansion. It's coefficient of thermal expansion. It is coming from the gravity term. So if you remember the Navier-Stokes equation as V dot del V equals minus gradient of P plus mu del square V plus rho G in vector form, right? And I guess you have a rho there. So that rho is expanded as a linear function of temperature because the density depends on temperature. And if you are heating it, that means the fluid will become lighter, and in a gravitational field it will rise as a buoyant plume. Okay, so this term basically captures the buoyancy term. Now I have put G1 and G2. What do they represent? They represent the components of G in the x1 and x2 direction. So if I say that G is pointing in this direction, that would mean I have G2 as being equal to G and G1 is equal to 0. Okay. Now in our analysis for the horizontal plate, we are going to consider only the forced convection. So this term would be called the natural convection as well. Natural convection mechanism. later on, if there is time, we will look at a problem where I have a vertical plate that is heated. Okay, in that case, you will have a boundary layer that forms that will be due to natural convection alone. Okay, it's not a pressure-driven flow. So the theory behind it, the mathematical techniques are all exactly the same, except this term will be present, but the pressure term won't be present. But I'm putting both the terms here, but very soon we are going to look at only forced convection, where I'm going to drop the buoyancy term. I'm just showing you that it is there. Okay, and the next equation is the energy balance equation, where the left-hand side is what? Is the convective term. Whenever you have velocity, the velocity carries energy with it. Okay, so that's a convective term. The right-hand side, the first term is the conduction term. What is this term? The third term. Viscous heating, viscous dissipation, heat generation. What would be the last term? If there is a reaction at the interface, like if the plate is a catalyst and there is a species that is diffusing to the surface, reacting, and then coming out, okay, then you will have a heat of reaction term, possibly. Okay, so this would be something like heat of reaction. Okay, and the next equation is the same thing for mass balance. So you have a convective mass transfer on the left hand side, diffusive mass transfer, and RA would be the reaction term. That makes the species A either appear or disappear. If A is a product, then it will be a source term. If A is a reactant, it will be a sink term with a negative sign in front of it. Okay, so that is the complete transport equations that couples fluid mechanics, heat transfer, and mass transfer with possibly a chemical reaction. Any questions on that? And all we have done is we have imposed the two-dimensionality. So we have cancelled other terms that are not varying in the direction perpendicular to the board. And now we need to do the careful scale analysis. I'm not going to do as in detail as we did for the flow problem. Okay, but the arguments are very similar, and you will end up with very similar equation. So to simplify the problem, as I said, we will take only one mechanism at a time. Okay, first we'll look at forced convection, then we will look at natural convection, then we can look at mixed convection, where both are present, and from horizontal, vertical, we can look at even an inclined plate. So the theory behind it all exists, and these are all discussed in detail in the book by Schlichting on boundary layer theory. So in this particular example, the figure that I've taken from Bird-Stewart and Lightfoot, you actually have the plate and the boundary layers are shown on both sides. Okay, so there are two boundary layer thicknesses that are shown. So this one is the delta, which is the momentum, and this one is labeled as delta T, that is the thermal or the heat boundary layer. Okay, so for example, if you look at the velocity field changes in the boundary layer, and then it becomes constant outside of it. Okay, and if you look at the temperature field changes like this, and then it becomes constant outside. Okay, so what we are saying is that there are two small regions, one which confines the momentum diffusivity, the other one that confines the heat diffusivity or the heat conduction. Now, how would this temperature profile look? I guess here he's Bird-Stewart and Lightfoot, they're plotting T0 minus T and T0 minus T infinity. So at the plate, T is equal to T0. So the temperature is 0. It's already a scaled temperature. And as you go farther away, T0 minus T infinity is a finite amount. Okay. Let me show the equation again. I don't know whether I have it down here. Okay. Okay, I guess maybe let me defer the question a little later. Okay, so there are two boundary layers, and if you have mass transfer also, there will be a boundary layer corresponding to that. That is the region over which concentration change occurs. So thermal boundary layer, you should think of as the region over which temperature change occurs. Outside of the boundary layer, temperature is constant. Momentum, yeah.
Is it always that delta T is smaller than delta?
That was the question I was going to ask you. You preempted me. Okay, we will think about that. It's a very good question. Will delta T be smaller than delta, larger than delta, equal to delta? What does it depend on? We need to understand that. That's a very good question. Okay, but we will address that very soon. But before that, I wanted to show for the natural convection, for example. These are some of the sketches. For natural convection, again, now in this case there is no forced flow. What you have is a plate that is heated and there is fluid surrounding it. Okay, so what would happen? So the fluid is going to be zero at the wall. It's going to increase and then it's going to be stagnant. So there is no flow outside of the velocity boundary layer. Okay, all the flow occurs only near the plate. And the thermal, so this is delta and this is delta T again. So within the thermal boundary layer, the temperature profile is going to like this, and outside of the boundary layer, the temperature remains constant. Okay, that's how the boundary layer will look like. Once again, the same question applies. Is delta T larger, smaller, or equal to delta? What does it depend on? Okay, and here is a sketch of a concentration boundary layer. The same idea. Okay, so this would be delta C, and you will have another one that is delta. Okay. Now we wrote down the full equations here. Okay. So we need to do a scale analysis by introducing the scale factors exactly the same way that we did before to show that this term becomes small, this term becomes small, and all the terms in the second momentum equation, the x2 momentum equation, are small. Okay. That we have already done, so we're not going to repeat that again. Okay. But I'm just going to reintroduce the same scales that we did, meaning that the scale V is an unknown, the scale delta is an unknown. We need to introduce another scale delta T to scale the temperature equation. So these are not, in general, they are not the same. And of course, pi is the pressure scale. And the temperature is non-dimensionalized in a couple of different alternate ways. TW minus T divided by TW minus T infinity. TW is the wall temperature, T infinity is the faraway temperature, and I would prefer to do this for a hot wall. And I prefer to do this as T minus T0, T infinity minus T0 for a cold wall. Why would that be? Because I want theta to be, my dimensionless temperature to be positive. But they should scale between 0 and 1 in both cases. Okay? So when I put T equal to TW or T equal to T0, I will get 0 at the wall. And as I go far away, T infinity, I'll get 1. So theta will be scaled between 0 and 1. That is our idea. We want to scale every independent variable, the dependent variable, as well as the independent variable to be between 0 and 1. Okay, the scaling arguments are very similar to what we did before. But we are going to ignore the heat generation term. What is the number that characterizes the viscous dissipation? Do you remember? It's called the Brinkman number. Okay, we did that, I think, one of your problems. And the Brinkman number is assumed to be small. It's not 0, but it's assumed to be small. And similarly, gravitational buoyancy force is assumed to be small. That means the Grashof number is assumed to be small. And we are considering a flat plate. Okay, so the velocity outside of the boundary layer is a constant. Under these assumptions, if you go through the scale analysis that we did, you will get exactly the same equation as we did before for the flow. And for the energy equation, you will get the convective term and only the diffusive term in the x2 direction. The diffusion in the x1 direction is small compared to convection. So it is convection dominated in the x1 direction, and it is balanced by diffusion perpendicular to the plate. And that's what physically this term says, this equation. Okay? And they are subjected to the similar type of boundary conditions. At the entrance, we have free stream velocity. At the plate, you have no slip and impenetrability. And as you go far away, the stream again is free stream velocity. Same thing for temperature. At the plate, x1 equal to 0. Sorry, at the entrance. This is at the entrance. x1 equal to 0. It's coming in with a uniform temperature of T infinity. And at the plate, x2 equal to 0. You have T0, the wall temperature. And as x2 goes to infinity, once again it reaches the free stream temperature. So we need to solve these coupled partial differential equations subject to these boundary conditions. The question that I guess I would like to ask at this time is to probe the question that you raised. Okay. Before that, let me ask you, what is the nature of coupling? Does fluid mechanics affect heat transfer? Does heat transfer affect fluid mechanics? Do you need to solve all the equations simultaneously, or can you solve for some equations first and then the other equations next? Do you understand the idea of coupling, right, between equations? If every equation depends on every other variable, that means you need to solve them simultaneously. Okay? But if you have a set of equations that are self-contained, but their output depends on the other equations, then you will call them a one-way coupling. Okay? So in this particular case, for example, you must solve these two simultaneously. V1 and V2 appear in both the equations. They are coupled, okay, and they are nonlinear because you have V1 and the product of V1, okay, and we know how to solve them. Blasius solution. Introduce the stream function, introduce the similarity variable, and these can be reduced to f triple prime plus 2f f double prime equal to 0. That's the Blasius solution. Okay. To that, we are adding this energy balance equation, and the energy balance equation is affected by the velocity field because V1 and V2 appears here. So after you have solved for V1 and V2, you can plug them in there. But the temperature does not affect the flow field. Why? What assumptions did we make that kind of cut off that link? Small Grashof number, buoyancy effect is negligible. Okay. So immediately what you should recognize is if the buoyancy effect is there, then the equations become completely coupled. So the temperature will affect the flow will affect the temperature. All three must be solved simultaneously. But in this case, we can solve them sequentially. First two you can solve together, and then you can solve the energy balance equation. Now, what is the physical meaning of this quantity nu and alpha? Remember, alpha is thermal diffusivity, K over rho Cp. Now the rho Cp comes from the left-hand side because we have this multiplication factor rho Cp for the convective term. Similarly, you will have a rho here that was divided by mu. So mu over rho. Mu is nothing but mu over rho. So the physical meaning for momentum diffusivity is it's a diffusion meter square that the diffusion passes through per second. So both of them will have the same units, meter square per second, meter square per second. Okay? So thermal diffusivity in a similar sense is the distance over which heat is diffused by molecular processes over a given unit of time. If I make alpha is equal to nu, what do you think would happen to the delta T and delta, thermal and momentum boundary layers? Why do you say that? The equations look identical, right? If I replace alpha with nu and V1 with T, I don't know the difference. Okay, so the solution must be exactly the same. So, yeah.
Just a question, a general question.
Yeah.
Does the Lewis number have anything whatsoever to do?
Not quite, but you are thinking in the right direction. There is a dimensionless number. It's not called Lewis number. It's called Prandtl number. Nu over alpha is a dimensionless number. It is a property of a fluid. Okay, because all the quantities that appear in there are properties. So there is no control over it. So Reynolds number is something that we control because it's a velocity in there. We can change the velocity. But this one, if you're given a fluid air, you're stuck with it. Air has a Prandtl number of 0.73. Okay, so it's a property. So the next question to ask is, okay, mathematically it's nice if nu equals alpha and Prandtl number equals 1. But boundary layer, I don't need to solve. I can take the Blasius solution and construct the temperature profile from the same solution, because it's the same equation, right? This is where the analogy comes in. The undergraduate level, you might have seen Chilton-Colburn analogy. There are many analogies that between heat transfer, momentum transfer, and mass transfer, which simply means that if I know the friction factor, I can predict what the heat transfer coefficient is. Or if I know what the heat transfer coefficient is, I can predict what the mass transfer coefficient is. The reason is the underlying equations are exactly the same for the three transport processes. Okay? Did you have a question?
Yeah. I can't read like T(x1 = 0).
Oh, near the entrance. This is why I don't prefer to write, I prefer to type it out. My handwriting is, no, I'm sorry, my handwriting is terrible. If I come to the board and write it, it'll be very difficult to follow after a while. And it probably is the same even in here. But at least you have a clean notes with you and you can make the mess out of it. Okay? Yeah.
I don't understand. If you color the first two equations, we will have two equations and the two unknowns, V1 and then V2.
Yeah.
If we have the first and the third equations, we will have three unknowns.
No. All the equations are, if you couple the, if the whole problem has three unknowns, V1, V2, and T, and we have three equations. Okay? So how we can solve it, you look at the structure of the equation. So it's seen that the first two equations depend only on V1 and V2, does not depend on T. So you could solve for it for V1 and V2 first, independently, without solving the energy equation. And then you need to take that V1 and V2 and put it in here, because V1 and V2 appears in the third equation. So the temperature profile is affected by the velocity field, but the velocity field is not affected by the temperature field. Okay?
The second one is not linear, and the third one.
That's a good observation. Yeah. It is nonlinear, and the third one is linear, right? But once you have solved the second, the first two equations, coupled nonlinear equations, using the Blasé solution, you will find that the third equation is actually linear. It's easier to solve. You still need the table that we saw from Blasé's solution, because we will need the V1 and V2. V1 and V2 are given from Blasé's solution. But it's linear, so it makes it easier to solve. We will see the ways of solving this. We are going to see two ways of solving it. One is something equivalent to Blasé's solution, the regress method, the analytical method, which is called Paul-Hausen's method, because he developed the solution. The other one is one common integral method, where you don't get the temperature profile, but you need to assume a temperature profile. Both will give you the same result. What is the result that we are after? Why are we solving this? We want to predict the Nusselt number. We want to predict the heat transfer coefficient. Okay, so that's the goal of this analysis. Any other questions? So yeah.
You said like the second one, the third one, they are identical. So the boundary layer, if that two are the same, the boundary layer could be the same.
Right.
The equation is not very similar, because the second one is non-linear and the third one is linear.
Okay, that's a good point. But what you need to look at is in terms of the physical mechanism. Okay, so the second equation is essentially V dot delta operated on V1, and there is a rho there, which we took it out. Okay, is equal to mu times del square V1. And if you take the third equation, it is the same thing, V dot delta operated on T. There is a rho Cp there, equals K times del square T. When you look at it this way, the operator that is operating on rho V1 is the momentum convection. That operator is the same, right? And that's why the solution is going to be the same. So what we are saying is, if you give me a matrix A, okay, and I operate it on X and I get equal to B. It's a linear system of equations, for example. Okay, if you have another matrix B times Y equal to also B. Now, if A and B are the same matrices, same operators, and the forcing term is the same, then the solution X and Y must be the same. right? So that's the kind of argument that we are making, that the operator V dot delta that operates on rho V1 is the same that also operates on rho CPT. Okay, so the convective process for momentum is the same as the convective process for energy, and the diffusion process for momentum is the same as the diffusion process for energy. So there is a one-to-one correspondence between the velocity profile that you will get for V1 and the temperature profile that you will get for T. Even though you are right in the sense that this V1 also appears here, making it nonlinear, whereas here it is T, and that makes it linear. So one is a nonlinear equation, the other one is a linear equation, but the solution profile is governed by the same operators, the same rules. So the same profile, another way of looking at it is, if you give me a profile for V1 and I plug it in this equation, that equation is satisfied. So I know the solution. So if I take the same profile for T and I plug it in, it should also satisfy that equation. Did you?
I have another question.
Yeah.
What is the process of like the thermal convective term in the thermal convection in the thermal
Convection process in a,
yes.
in a
Like the boundary layer of the thermal boundary layer
Yeah.
can be smaller than the momentum.
yes. When would that happen? That's the next question.
Why I cannot imagine why this, they are not the same.
It's an easy question to answer, because what you need to do is you need to think about the two properties that determine are alpha and nu. So if you find a fluid that has nu, the kinematic viscosity characterizes the ability of the fluid to transfer momentum in a transverse direction, perpendicular direction. And thermal diffusivity characterizes the material's ability to conduct heat. Both are molecular processes, okay, but they both don't occur at the same rate. And that's why we have different properties. For the same fluid, water, the diffusivity, the thermal diffusivity is not the same as kinematic viscosity. Okay, so that means that a fluid that has a higher kinematic viscosity can send its impact deeper into the boundary layer. Remember, the boundary layer thickness is proportional to the kinematic viscosity. So honey will have a thicker boundary layer than air, right? So it is basically proportional to that transport quantity. The transport quantity happens to be diffusivity, thermal diffusivity, then you can say the ability to transfer heat depends proportionally on alpha. And because most fluids don't have the same property values, that is, Prandtl number is not 1, you don't have the same boundary layer thickness.
So can the thermal boundary layer be thicker than the momentum boundary?
Yes. So having this discussion, what would you answer? When would the thermal boundary layer be thicker than the momentum boundary layer? When would it be thinner than the boundary layer, the momentum boundary layer?
Depending on the Prandtl number, when Prandtl number is greater than 1, the diffusion of momentum number will be thicker and
Exactly. So that's the key. Prandtl number is nu over alpha. If Prandtl number is greater than 1, that implies nu is greater than alpha. That means the momentum boundary layer will be thicker than the thermal boundary layer. If Prandtl number is less than 1, that means nu is less than alpha. So the momentum boundary layer will be thinner than the thermal boundary layer. Now, what is the nature of these numbers? These are basically things that we have summarized here. Here is a table I just pulled out from one of the sources that gives you the Prandtl number for various materials. Okay, the first table is basically for liquid metals: mercury, bismuth, potassium, sodium in the liquid state. So that means they must be, except for mercury, all the others are at fairly high temperature, because you need to treat them in its molten state, in a liquid state. Okay? And you'll find that their Prandtl number is very, very small, of the order of 0.01. Okay? And that means nu is much smaller than alpha for these cases. air, most of the gases, carbon monoxide, here you have air 0.07, carbon monoxide 0.73, nitrogen 0.716. Okay, so in this case, nu is of the same order as alpha. Prandtl number is very close to 1. So for such material, you will find the two boundary layers to be very close to each other. So in here, you will find delta T to be much larger than delta. Then you have material of the other end of the spectrum as well. Prandtl number for liquids, ordinary, not molten liquids, but ordinary liquid, like engine oil, 6,400. Okay, glycerine, 6,700. Okay, even water is about 5.8. Ethylene glycol, 151. So there is a whole range of material behavior for Prandtl number. It is a fluid property, and you could have any values, very small or very large. Okay, so in this case, Prandtl number is much, much larger than 1. That means nu is much, much larger than alpha. That means delta is much larger than delta T. Okay, any questions? Physically, do you understand? Yeah.
Why do some of them have two values? It's because it's temperature dependent. In the first.
Yeah, there are two different temperatures, right? Yeah. So 422 versus 977. Yeah. So the properties are all temperature dependent, right? So nu and alpha. So that's why. Yeah. Okay. All right. So we have already seen gaseous solution, so we know what the similarity transformation is that converts that partial differential equation into an ordinary differential equation. That is eta equals x2 divided multiplied by square root of u over mu x1. So that leads to the Blasius equation after a lot of algebra, which we have seen in detail in the last class. So the boundary conditions then also transform. This kind of a similarity transformation you should be able to do. Okay, transform the PDEs as well as transform the boundary conditions to a consistent set. We have 4 conditions that they transform to a consistent set of 3 conditions. Now for energy balance equation, we said we are going to introduce theta as a dimensionless variable, and here I've written this as nu divided by Prandtl number. Okay, so if Prandtl number is 1, you can see in fact nu is the parameter that appears there, and the similarity is exact. Okay, so we need to, so right away we know that this theta that we are talking about is going to be a function of eta, and it's going to be a function of Prandtl number as a parameter. Different values of Prandtl number will give you different temperature profiles, and so we need to be able to calculate the whole class of solutions for that. But the same similarity transformation would work. Okay, and I've shown you a key step in that. That is, let me just map this for you term by term. So here you have, for example, V1. Okay, V1 in terms of the similarity variable is f prime, and then I have d theta dx1. Okay, d theta dx1, which is what I'm going to write using chain rule as d theta d eta dx1. I can find out what d eta dx1 is because I have the defining equation for eta, which is this equation. So from this I can take the derivative of eta with respect to x1. Okay, and similarly for V2. V2, if you remember from the previous lecture, is this entire expression. Okay, and then you have again d theta dx2, and that is written as d theta d eta dx2. And on the right hand side, let me recycle this symbol color. So it's d square theta dx2 square, that is d square theta d eta square times d eta dx2 square. Okay, so you need to work these two through yourself. Okay, at least once, and then you cancel and simplify things, and what you will find is that equation simplifies to a second order ordinary differential equation for theta. So the similarity transformation, the same similarity transformation works for the thermal boundary layer equation also, except you have a new parameter that is appearing in there, and you have f. What is this f? is the velocity field. Remember, the Blasius solution is given by f triple prime plus 2f f double prime equal to 0. So when you solve that, you have solved for the flow field. Then you know f, f prime, f double prime, so you know all the velocity fields. And these are all depending on the velocity fields, for example, f prime, etc. So the flow field shows its impact or dependence in here. F represents the flow field, PR represents the Prandtl number, theta is the unknown. And you need to subject that to the boundary conditions, which is theta at the wall is 0 and theta at the edge of the boundary layer is 1. Now, as you said, this is a linear equation, right? Why do we call it a linear equation? The unknown is theta, and there are no products or nonlinearities with theta. F is a known function. F is a known function. How do we know it? We just know it as a table. Okay, F is a function of eta, and Blasius solution gives us a table of F at various values of eta. Okay, so we need to put that in and then solve this equation, a linear equation for the temperature profile. Okay, how do we do that? Well, we take this equation and write it as move this to the right hand side, minus PR over 2f prime, and then we will have theta prime, but bring the theta prime to the left. So this is d eta of theta prime, which is nothing but theta double prime. But I'm writing it in the way that I can recognize theta prime as the variable. Okay, same trick that we used in solving the Stokes problem as well. Okay, so then you can, the main thing to understand is that this is a separable equation. That means d eta can be taken to the right hand side and written as a quadrature, as an integral. You can separate that. And then d theta prime over theta prime is, integral of that is log theta prime, right? And then you're taking the exponential of that to move it to the right hand side. So you get theta prime as equal to C1 times exponential of minus PR over 2, integral 0 to eta f of d eta. Now remember, f here is a known function. So if you plug in the expression, you can evaluate the integral. But it is a complicated expression. So it's not easy to analytically evaluate what that is. It has to be done numerically. You have to evaluate using trapezoidal rule, Simpson's rule, something like that. You can evaluate this entire integral. Okay, so that gives you the first derivative for theta prime. Now once again, write this as the same as d theta d eta, and separate one more time. Take the eta to the right hand side and integrate one more time. So you actually get, there is an integration constant, of course, here, C1. Okay, so integrate one more time, you'll get C1 times a second integral, integral 0 to eta of the exponential of minus PR over 2, another integral 0 to eta f of eta d eta, plus a second integration constant. Okay, so that is your analytical expression for the temperature profile. And we need to now evaluate the two boundary conditions C1 and C2. Obviously, when at the plate, when eta is equal to 0, what is the integral? Integral from 0 to 0 would be what? 0, because it's area under the curve, but there is no limit. So it's the same point. Okay, so that means 0 is equal to C2, because the integral itself will be 0. Okay, so that tells you that C2 is equal to 0 from one of the boundary conditions. From the other boundary condition, you can evaluate C1, but this has to be evaluated from 0 to infinity over the entire boundary layer, because at the edge of the boundary layer, we know that the temperature is equal to 1. This theta becomes equal to 1 at the edge of the boundary layer. So the C1 becomes 1 divided by this entire integral, with eta being infinity. Now you have to be very careful. If I ask you at this stage, go and evaluate this expression, how many of you will be able to do that? You have to interpret that very carefully. This is the temperature profile. I say Prandtl number is equal to 0.7 for A. Go and construct the plot for a temperature profile. What would you have to do? So I've given you Prandtl number, and I want a plot of theta versus eta. And I know that eta is initially, theta is 0, and at this point it's going to be, as eta goes to infinity, it's going to be 1. So the profile is going to be something like this, perhaps. Okay, but I need to construct that curve because that curve is represented by this equation. My question is, how would you go about doing that? What would you need to do? What information would you need?
The Blasch's solution, you take that table and put different values of eta, will clarify what different values of eta.
Exactly. So I have to give you the table. So, and if I say for eta of 0.1, you will put this limit as 0.1, okay, and find that integral up to that point, and put that again into that expression, the whole expression, and do the integration again. So there are two quadratures that you need to do, two integrals that you need to do, and the bottom one is going to be a constant, a number, because that integral is always from 0 to infinity. It will remain the same for all the cases. But the top one is going to change depending on eta of 0.1, 0.2, 0.3, 0.4, etc. Okay? So that has to be done carefully in interpreting that. Okay? Of course, this is valid for Prandtl number less than 1, Prandtl number greater than 1, because we didn't make any assumption about Prandtl numbers. It's valid for all Prandtl numbers. That's the most general solution, equivalent to Blasch's solution, called the Paulhausen method. And here is a solution for various values of Prandtl numbers going from 0.7 to about 1,000. That is from air to glycerin material like that. And you find what happens to the temperature profile. They are plotting the temperature on the x-axis, so it goes from 0 to 1. And this is going from 0 to infinity. But 6 is good enough because it almost flattens out. So does that graph make sense? Now, in Bird, Stewart, and Lightfoot, this problem is not, the full solution is not done in Bird, Stewart, and Lightfoot. So I took this from a different book. But Bird, Stewart, and Lightfoot have just one example for large Prandtl number limit. Okay? And in terms of the final exam, I will hold you responsible for anything in Bird, Stewart, and Lightfoot, but not necessarily things that are taken outside. But I'm presenting them so that it forms a complete picture. You understand what is the total solution and what are asymptotic solutions. This one is an asymptotic solution valid only for large Prandtl numbers. Okay. So what does large Prandtl number mean? As we talked about, if Prandtl number is much larger than 1, that means nu is much larger than alpha. Okay. So that means what? The boundary layer thickness, delta, is much larger than delta nu is larger, means delta is larger than delta t, right? So let's sketch that so that we understand what's happening. So this is the plate, and that's delta, and that's delta t. Delta is much larger than delta t. Okay. So previously we obtained the solution using proper velocity field over the entire boundary layer thickness. Okay. So it was valid for large Prandtl number as well as small Prandtl number. But when I make this assumption that the Prandtl number is large, is there any assumption that you can make about the nature of the velocity profile inside the thermal boundary layer? It's an idea that we have used, and these are the kernels of ideas that you should carry with you. The moment you see a problem like this, you should say, oh, I've seen this before, I've done this before. Same idea I can implement here. One of the problems that we did was when you had falling film, and we had mass transfer from the free surface to the liquid. Another case, we consider the mass transfer from the plate to the liquid. Okay, do you remember that? example?
When you linearize the velocity, you get the velocity constant.
In the case where we looked at mass transfer from the gas to the interface, we said I'm going to assume a velocity to be constant, right? In the case where we had mass transfer from the solid surface to the liquid, we said I'm going to linearize the velocity field. Okay, so this was the plate, and this is the interface, and the velocity profile is going to be like this. So when the mass transfer is occurring in this region, I'm saying the velocity is constant. The velocity affects the mass transfer equation. Just like here, the velocity affects the heat transfer equation. Okay? And in this region, we said, I'm going to linearize the velocity field. I'm going to replace this by a small straight line. Okay? So now, using that idea, what can you say about the velocity field inside the thermal boundary layer in here? The actual velocity field is going to be something like this, right? But if the thickness of the thermal boundary layer is small, I can say I'm going to approximate this by a straight line. The same idea. I'm going to linearize that boundary layer. So I'm going to take the Blasius solution, take a Taylor series expansion of the Blasius solution, and take only the first term, the linear term, the straight line. So I'm going to approximate the velocity field as a straight line. Okay? That's the idea. The whole problem is based on that idea. And the idea works only when the Prandtl number is large. Why? Because in that region, the thermal boundary layer is so small compared to the momentum boundary layer, we can make that approximation. Any questions on that? I guess.
The number is very small, then we can make the approximation to constant.
It's not constant because that's a good question.
After a while, the boundary layer is not.
That's true. It's a very good point. I never thought about it, but now that you raised it, let's discuss that. She's asking about the other limit. What happens when the Prandtl number is very small? Okay, so in that case, the thermal boundary layer will be something like this, and the momentum boundary layer will be something like this. So your point is that the velocity field is going to be something like this and then constant everywhere, right? So why can't we assume the velocity to be constant everywhere? Can we assume that? It's non-constant only in a very small region, right? That's your argument, right? How many of you would think that's a good idea? I don't know what the real answer is. It's a good question. I'm going to speculate, and this is what I want you to do too. You are graduate students. You should come up with an idea, and then you can verify whether the idea works or not. I have a concern in using that. I'll tell you what the concern is. That concern is that we are, after all, interested in predicting the rate of heat transfer from the plate. Ultimately, all this analysis is to predict heat transfer coefficient or the heat transfer rate or the mass transfer rate or the frictional force, right? So the heat transfer rate depends on what? It depends on the gradient of the temperature at the plate. Okay? So even though the temperature outside, the profile may be predicted very well by assuming a constant velocity, the temperature field inside will be influenced strongly by the velocity field locally there. And it is that temperature field, the gradient of it, that's going to determine what the heat transfer rate is. So at this stage, I would be very cautious of making that kind of an assumption because I might potentially introduce a large error. But really, I don't know the answer to that. It's a good question. I don't know the answer to that, whether it will give you the correct answer or not. Okay. Any other questions? Okay. Do you recognize this term? If you do, tell me what I've done to that equation. Well, you obviously recognize it as an energy balance equation. You have theta in it. This is the convection. This is the diffusion. What have I done to this term? That is the V2 term. So what have I done to that? How did I replace that by this? Exactly. continuity equation. Okay, so basically I took the continuity equation, separated the two terms, and integrated it once. We have used this idea once before, where one common integral analysis. Okay, when we are trying to satisfy and eliminate V2 from the continuity equation. Okay, so that is a continuity equation that replaces V2. So I have only V1 and V1, its derivatives. Now, linearizing the profile, this is the basic idea that we talked about. V1 over U is a linear function of x2, the direction perpendicular to the plate. Okay, and this you have to do, I have not shown the steps here, you have to do from taking the function f from Lassie's solution, which gives you the velocity profile, and do a Taylor series expansion on that. Okay, again, in BSL he doesn't do that, so make sure that you can fill the intermediate steps. If you have difficulty, come and see me. Okay, but this is basically the linearization step from the Blassier solution near the plate. And that says V1 is only a linear function of x2, and we are linearizing only in the x2 direction. Still, it is a function of x1, and it is an inverse quadratic function of x1. Okay, so only in the x2 direction we are linearizing. The linearizing coefficient turns out to be 0.332. You have to evaluate that from the Blassier solution. Now we have V1 that we need to replace here and we need to replace there by this linear expression, which is done easily because all you have to do is substitute in there and substitute in there, take its derivative, take its integral, go through all the math that is needed, and you will get these terms. Okay, so this is essentially CUX2. This is basically replacing it by V1 from here. And this is a more complicated expression because we're taking the derivative of V1, the linearized expression, which gives you a constant, then you're integrating with respect to x2. So you get an x2 square there. Okay, that looks like a pretty complicated partial differential equation. Is it linear or nonlinear? It's linear. Once it's linear, it's always linear, right? We started off the energy balance equation as a linear equation. It is a linear equation with a coefficient multiplying the linear terms that are functions of space, x1 and x2. So it is a complicated differential equation, partial differential equation. So the similarity transformation is different for this. So you need to find what the similarity transformation is. Okay. Again, in BSL, they just give you it is eta equals x2 divided by square root of x1. There is a constant that they throw in. Okay, don't ask me how you come up with it. You cannot come up with it if you're doing it for the first time. So, but what matters is the fact that eta is x2 divided by square root of x1. You can leave this as the entire thing as some constant gamma. You can figure out what gamma should be later on so that you end up with a simple equation. That's the key. The key is dump all the known constants into this expression so that you get a nice value, 3 eta squared d theta d eta. And that again is exactly the same procedure that we went for Blassier's equation. That is, take all the partial derivatives. So you will write this as d square theta d eta square times d eta dx2 square, etc. Every one of them you need to do that. Okay, by applying the chain rule and simplifying. Eventually you get this. In what way does this equation differ from the equation that we obtained for the general case? Remember, this case is for Prandtl number of infinity, large Prandtl number. Okay, maybe I should write down the previous one side by side so that you can compare the two. I'm assuming that you will fill in all the math in between. I'm just focusing on the physics and the interpretation of it. Okay, so the equation here was theta prime PR over 2 theta prime F. Theta double prime plus PR over 2 theta F, I think, right? Or was it theta prime F equal to 0. This is the general case. And this is as Prandtl number goes to infinity, large Prandtl number. What is the difference that you see between these two? Both are second order. course, they must be second order because we started off with a second order partial differential equation.
So doesn't have the velocity.
Exactly. Okay, so in this case, velocity, the total velocity field influences the temperature field. In this case, there is no velocity. Why? What happened to the velocity field?
It's dominated by the
We linearized. We put in an explicit expression for the velocity field, that it is a linear function. Here, this is a complicated function. We have to keep that function as it is. So when we integrate, we need to evaluate that quadrature. But now we are saying that replace f by a linear term, and that's why we get much simpler expression, which you can integrate much more readily and get an analytical result out of it. And the boundary conditions, when you transform that, basically the same as before. Theta is equal to 0 at the plate, theta equal to 1 as you go farther away. And integrating this is exactly the same procedure as we did before. Separate, because it's a separable equation, and you integrate twice, and you get the solution like this. Okay, so you still need to evaluate an integral, a quadrature problem you need to solve. The denominator is a constant, but that constant turns out to be a gamma function, a known number. Right? It's called a gamma function evaluated at 4/3. Okay, I think we are almost out of time. So that's the temperature profile that we could get analytically in both cases. In both cases, we need to evaluate a quadrature, but in the first case, there are two integrals embedded one inside the other that we need to evaluate. Here, there's only one integral because we use a known profile. We're going to take this in the next class and get what the Nusselt number is from this. Because once you know the temperature profile, you can take the gradient of the temperature profile to calculate the heat flux, and then you can convert that into Nusselt number. So let's just stop there. Please go through this section carefully. And I'm not covering mass transfer explicitly, but I'm going to let that as a reading assignment because it's a similar mass transfer boundary layer theory that you should also be familiar with. Okay? Yeah, we agreed that it will be on Tuesday and Thursday, starting 1 hour before. So 2:30 to we'll go till 5 o'clock. Next week is the last week, right? Now there is no. Pardon me? You are happy.
No, it's not bad. I'm just like, it's gone by so fast.
It's gone. I also felt that it got so fast. Yeah. So
I feel like
happy Thanksgiving, and expect one more assignment. I'll put it up sometime